Hello, welcome to this video. So in this video we're going to discuss for velocity. This will involve the idea of wordlines and tracing out particles through space-time. So we'll be describing what wordlines are, and wordlines are important both in the context of relativity but also in the context of string theory. Because string theory describes particles as one-way strings, but uses ideas in relativity to describe the dynamics of these strings. So understanding wordlines and also for velocity that comes from that is very important broadly, not just in relativity in and of itself, but anything that uses relativity, like string theory. So, if you would like to learn more about string theory, this is a good background video for that. So we'll be discussing what wordlines are, what for velocity is, and also looking at what the Lorentz invariant quantity is associated with the length of for velocity, because for velocity is a 4-vector, so the length of a 4-vector is a Lorentz invariant, and so different observers which are moving relative to each other still agree on the length of this 4-vector. And as we'll see, this length turns out to be the speed of light. And we'll finish this video with a kind of little challenge I've got for you if you would like to kind of have a go at working out something yourself and playing around with some of the ideas covered here to make this video more interactive and to hopefully kind of like encourage discussion and stuff within the comments or within kind of the community of viewers. So before we look at the path we'll take in this video to help kind of guide you as to what route will be taken to understand wordlines and for velocity, it's worth considering why wordlines and analysing them, such as talking about for velocity associated with them, are important. Well, in the context of relativity, any particle will seem to trace out a path which in space-time is called a wordline. So for example, if one is looking at, say, a moving car and one is stationary, one will observe that the position of the car in space changes, and obviously time kind of ticks along. And so the car moves into the future, and so the car in a sense has motion in time. And since the car is motion in space and time, it has motion in space-time. But also objects that are stationary relative to you will move forwards in time along with you. And so even stationary objects have a trajectory through space-time. And this trajectory is described visually in terms of a wordline. So understanding relativity requires kind of understanding how objects move through space-time, and an important part of visualising this is the idea of wordlines. And the other thing is you can actually get to the equations, the relativistic kinematics of kind of moving particles by considering invariant quantities associated with these wordlines. And so in terms of kinematics, which is very important if we're considering how particles kind of behave and interact if they're moving very quickly, the idea of wordlines is very important. Also, as well as wordlines being important in and of themselves, if you generalise that in the context of string theory, you start to describe world sheets. So, whereas often in physics, and at least as much as we've been able to experimentally verify this approach seems to work, we often consider particles as objects which are essentially point-like, or in other words, zero-dimensional. String theory is a very speculative idea based on the idea that, well, a particle might seem to be point-like, but that might might just be because we're not really looking at small enough scales. If we were to look at small enough scales, we would actually see that the particle is extended across space. And the simplest way it can possibly be extended is if it's extended in one dimension of space. In other words, the particle forms a string. And string theory is about how the different types of particles are actually just different motions of this kind of fundamental string. So electrons, protons, quarks are just the string vibrating differently. And so it's really beautiful geometrically. It also turns out that string theory may be a candidate for quantum gravity. The heyday of string theory is somewhat over. String theory as kind of a popular suggestion in theoretical physics kind of faded away during a period known as the String Wars. Slightly melodramatic name, but still, string theory is a very rigorous and pretty well understood speculative suggestion for kind of the behaviour of particles at really, really high energies. Because at really, really high energies you probe really, really tiny distances, and therefore the string dynamics of these particles, if particles are strings, would become observable. Part of the difficulty with testing string theory is that you need to get these particles to incredibly high energies for their string nature to become apparent, if indeed they are essentially strings. But the energies we're talking about are colossal, far bigger in terms of many, many orders of magnitude to the kind of energies we can currently get particles to. So for now it seems to be a very speculative suggestion, but maybe it does have indirect effects that we have yet to test. If string theory is true, for example, it may well have a large impact upon black holes, because in black holes space-time is stretched very significantly, and that stretching itself corresponds to having huge amounts of energy content in a small region, and that may well make the string nature of matter quite apparent. But to understand string theory, one has to understand the dynamics of these strings, and you get out the dynamics by starting with an action and using Hamilton's principle of least action to derive the equations of motion. But the action for string, at least a relativistic string, is actually associated with the area of the worldsheet. So ultimately, to understand the dynamics of strings and that string theory, you need to understand worldsheets. But worldsheets are a natural extension of the idea of a worldline. So, whereas a particle as a point-like object traces out a worldline in space-time, a string would trace out a worldsheet. Because a string is like one dimension space, and as it moves through time, it will therefore form a two-dimensional surface, which we call a worldsheet. So, if you're interested in string theory, this video might also be good background. But now we talked about why worldlines are significant, I'm just going to briefly go through the structure of this video before we jump right into a discussion of worldlines and the associated idea of four velocity. So, before we go into the full detail of the video and talk about worldlines in detail, it's worth talking about the journey we're embarking on, which will get us eventually to a discussion about how the size of four velocity links to the speed of light, and I'll finish with a fun challenge to hopefully make this video fairly interactive. So firstly, we'll introduce the concept of a worldline, and talk a bit about what the components of forward position are, and therefore how a worldline shows the change of forward position. of a moving object from the perspective of a stationary observer, at least. And then once we talked about the world line, we'll have an idea for how forward position changes and how we visually represent that. So then we can talk about the rate at which it changes, and this will bring us to the idea of tangent vectors to the world line and defining carefully forward velocity. Then we'll use our definition of forward position, which we've kind of covered a few times in previous videos, to then find the components of forward velocity. Thinking of forward velocity as the rate of change of forward position, but we'll be very careful what time we're using to measure the rate of change when defining forward velocity. Something you always have to be careful with in relativity. We saw on our video E equals mc squared, when deriving it we have to be careful what time we're using to measure the rate of change. It's similar when we're defining forward velocity. Whenever you're doing relativity, you have to be careful what time you're talking about, because of things like time dilation. Time doesn't move at a universal rate for everything, everywhere, so you have to be careful with what time you're using, and that's something we'll talk about in detail when we're talking about forward velocity. And then we'll look at seeing how the size of forward velocity is related to the speed of light, and that will kind of mostly conclude our video, although there'll be an extra kind of like challenge at the very end to hopefully kind of encourage some discussion within the comment section or kind of within the community more generally, and hopefully make this video slightly kind of interactive, and give you something to play with if you'd like to use this video to have a go at thinking about, well, what if we defined forward velocity differently? What kind of things might we end up with? So that's kind of the road we're embarking on for this video. So now we talked a bit about forward position being the kind of the root of the notion of forward velocity. Let's have a go at seeing how forward position changes, and this is associated with the idea of a world line. So if you're a stationary observer, or you class yourself as stationary anyway, you might look kind of outside and, for example, see a truck moving. And the truck will move through space. And to simplify it, we can consider the truck moving along a kind of straight road, so it's moving along one axis of space. And the truck is obviously moving into the future along with you, and so it's moving in time. And then, so you can kind of describe how the truck's position in space-time, that is its position in time and space, will change. And in general, you'll end up with some kind of curve. And there aren't really many physical restrictions of what this curve can look like. If the truck has real rest mass, then the velocity of the truck will never reach or exceed the speed of light. But apart from that, there aren't really many limits on this trajectory through space-time. So in general, you end up with some kind of curve, and it can look fairly wacky like the black line, but it could be something much simpler. And as I say, this curve, well, each point on this curve has a vector which links the origin to that point, and that vector is for position, with a time component and a space component. Remember here, c is the speed of light, which is the same for all observers, so we can treat it as a constant. And it's also here to make the units of the time component still the same as the units of the space component. Now, if we're thinking about for velocity, we want some way to measure how this forward position is changing. So the change in forward position is shown by the whole trajectory. And the rate at which this is changing is going to be naturally some kind of tangent vector to the curve. It's a tangent vector because the velocity of a particle, whether it's the velocity in space or in space-time, is always going to be parallel to the direction the trajectory is going in at that point. So by definition, velocity has to be a tangent vector because velocity is in the direction in which the particle is currently moving. And therefore, since it's a tangent vector, in some ways it's measuring the gradient of the trajectory. So for velocity will be some kind of tangent vector to the world line, in other words the trajectory traced out by the changing forward position of the moving truck. Now, time in relativity is not something that all observers agree upon. The rate of time can vary depending on what observer is measuring the rate of time. And therefore, if we're saying forward velocity is the rate at which forward position changes, then we need to understand what time we're using to measure this rate. And because there are various possible times we can pick, time is not some universal quantity. Time becomes a parameter. And particularly when this curve is naturally, at the moment in the way we've written forward position, this curve shows how forward position changes, but changes with respect to time t. So time from the stationary observer's perspective. So time from your perspective as you're watching the truck move. But we can pick other times, and providing this other parameter has a unit of time, if we differentiate forward position with respect to that parameter, we will still end up with some kind of velocity through space-time. And one parameter we could pick, fairly natural parameter, is time from your perspective, so time from the stationary observer's perspective. That would make a fair amount of sense. That way, for example, the space component of forward velocity would be just dx by dt, in other words, the velocity of the object through space from your perspective. So if we chose the parameter we're differentiating forward position with respect to be time from your perspective, we would get a sensible forward velocity, like the space component forward velocity will match the velocity you measure the truck as moving it through space. So we could pick time from your perspective as a good parameter. But there's even a better parameter we can use. And that parameter is proper time. In other words, it's kind of talking about time as it seems to be passing for the truck, if you were to say look at a clock on the truck. And the passage of time according to the clicks of that clock, which is on the truck and therefore moving relative to you, turns out to be actually a better parameter. Because if we use that, in other words, if we use proper time, then we'll get a forward velocity which is actually Lorentz invariant. So both you and the truck would agree on the value, would agree on, I say forward velocity is Lorentz invariant, I mean the size of fall velocity will be like Lorentz invariant. So both you and the truck, or say a person driving the truck, would agree on the size of this fall velocity. So in other words, we define fall velocity to be the rate of change of fall position, but the rate is measured via time as you would observe it by looking at how the truck's clock is ticking. So not how your clock is ticking, but how the truck's clock is ticking. So it's kind of, it's how quickly fall position changes, but the fall position is kind of what you measure for the truck's fall position, but the rate is what you would see for a clock that is kind of ticking as the truck moves along, if that clock was on the truck. And that's kind of the nuance with fall velocity. It is a measure of how quickly fall position is changing, but it's not measuring how quickly fall position is changing from, according to your own measure of time. It's measuring how quickly it's changing according to, a clock that is on the truck. Or at least if you watch the truck and the clock, how quickly that clock would seem to be ticking by. So I talked about fall velocity fairly generally, and I made a comment about fall velocity which is strictly only true in special relativity, where often we're not worrying about acceleration. And that statement was that the size of fall velocity is a Lorentz invariant quantity. But if we're in special relativity, we are placing heavy restrictions on what the world line through space-time can actually look like. Particularly in special relativity, we're generally assuming no acceleration, and therefore most of the time at least we're considering, say, a truck which is moving at a constant velocity. So as you watch the truck doesn't seem to be accelerating or deaccelerating. And because of that, the truck is moving in essentially a straight line through space-time. It's straight, and I put that in quotation marks, because it depends on your notion of straightness, and because space-time is hyperbolic in its geometry, the idea of straightness is somewhat complicated. But essentially, if we were going to plot the world line, the world line would look straight, because the truck is moving at a constant velocity through space. And also, since it's moving at a constant velocity through space, it's it's just moving nice and neatly through time. And because the world line is straight, that immediately tells us that the gradient of the world line is going to be a constant. And we've already said that fall velocity is a tangent vector to the world line, is in a sense measuring the gradient of the world line. So if the world line is straight, then fall velocity, at least the size of fall velocity, would have to be a kind of constant, because the size is talking about the gradient of this world line. And that's partly, and whether you use time, as in time from your perspective, or time from what you would see if you were looking at a clock on the truck ticking by, both times would give you a fall velocity which would be, well, the size of fall velocity at least would be a constant, so wouldn't be change with time, at least assuming there is no acceleration involved. However, using proper time also allows the size of fall velocity to be a Lorentz invariant. So something, all observers within special relativity would agree on. So that's the advantage of using proper time over time that you would measure if you were looking at a clock which is stationary relative to you. So, these things are important. We've got for velocity would be a constant, assuming no acceleration, no matter what time you used. However, using proper time allows for the size of full velocity to also be a Lorentz invariant. So now we've talked a bit about full velocity as a tangent vector to kind of trajectory describing how the full position changes. We're now going to look at finding the components of full velocity, and that will allow us to find the size of full velocity. But before this, we're going to need to look at the components of full position. Now, full position has a time-like a time-like component equal to ct, and a space-like component. Now, if the truck is moving along a straight line, we can consider its motion to be along one spatial axis, which I'll call the x-axis. So x is how far the truck has moved along this axis relative to the stationary observer. Or at least, x marks where the truck is at along this axis relative to the stationary observer. Now, if we're going to work out the kind of components of full velocity, our kind of initial difficulty is with differentiating our full position with respect to proper time. When we're doing that, one of our terms is going to therefore be, for velocity, c times dt by d tau, where t is time as we would measure time ticking by as the stationary observer, and tau is a proper time, so the time we would observe the truck seeming to notice to pass by. And dt and d tau are related by our gamma factor, our Lorentz factor, and that is a function of velocity, where velocity is the speed the truck is moving at, so dx by dt. And so, using the kind of time dilation equation that relates to t and d tau through the Lorentz factor, and our definition of full velocity as the rate of change of full position with respect to proper time, we get these components for velocity. So the first component is c gamma, gamma is our Lorentz factor, and the second component, so the space-like component, is dx by d tau. Now, dx by d tau is not the same thing as dx by dt. As our equation between d tau and dt shows, generally d tau and dt are going to be different. So dx by d tau is not the velocity the truck is moving at least, as you would define velocity in terms of the distance the truck is moving relative to you, divided by the time it takes the truck to move that distance. So dx by d tau is not the same thing as dx by dt. And therefore, it's helpful to define, a new velocity, v star, which we define to be dx by d tau. Now, v star still has units of velocity, because x still has units of meters and tau still has units of seconds. But it's different to what you would measure for the velocity of the truck. So I put a star above the v to indicate that. So using that notation, our forward velocity has a time-like component of c times the Lorentz factor, and the Lorentz factor is a function of v, so dx by dt, and then our space-like component is v star, which is dx by d tau. And the nuance really, if we're going to calculate the size of this forward velocity, is that the time-like component depends upon v, whilst the space-like component depends upon v star. And it's important to take account of that when deriving the size of this forward vector, the size of forward velocity. It's worth saying v star is not a common notation. It's just a notation I use to emphasize that the space-like component of forward velocity is distinct from the spatial velocity of the truck, at least as far as you as the stationary observer would measure it. So now we've got the components of forward velocity, we can move on to calculating the length. And it's important when we're doing that to remember that, v and v star are different. So we talked about the components of forward velocity. Now we're going to attempt to find the size of forward velocity. Well, we start by looking back at the components. So the time-like component is c multiplied by our Lorentz factor gamma. And remember, gamma is a function of velocity v. And the space component of forward velocity is v star, which is dx by d tau, which is different from dx by dt. Now, if we want to find an expression for forward velocity, initially we're going to have, for the size of forward velocity, initially we're going to have something that will naturally depend upon gamma, which depends on v, and will also depend upon v star. Because both v and v star affect the forward velocity vector itself. But ideally, when calculating the length of forward velocity, we would like an equation just in terms of v star or v. Now, because v is a lot easier to physically interpret than v star, v is just the speed of the truck according to the stationary observer who's describing the world of the truck. Because v is easier to physically interpret, I like using v personally rather than v star. So now let's have a go at relating v and v star with each other, where v is the velocity that you would associate with the speed of the truck. So v star, remember, is dx by d tau. If we want to bring in a dt instead of d tau, such that we can write v star in terms of v, then we need to use our time dilation equation, which is dt equals the Lorentz factor times d tau, and we can just kind of, rearrange that d tau is dt divided by the Lorentz factor, and substituting this in to our expression for v star, and also noting the fact that because the truck we're considering is moving at a constant velocity, so there's no acceleration, gamma, our Lorentz factor, is going to be a constant with respect to time, so we don't have to worry about differentiating gamma with respect to time or anything like that. We can just think of gamma as a kind of constant. It's not a Lorentz invariant quantity, but it is a constant. And bearing that in mind, it's very easy to show that v star is just the Lorentz factor gamma times v. Now we've got an expression that relates v star and v, although when we initially find the size of the forward velocity q, we're going to have as I say, gamma and v star, we can substitute gamma v for v star and end up that the Lorentz invariant quantity associated with the length of for velocity, so q, can be found through the equation that q squared, so the square of the length of for velocity, is equal to gamma squared multiplied by c squared minus v squared. Now you might notice that there's this eta, which looks like an n with an elongated n. This is just like elongated n, I should say. The eta is referring to the Minkowski metric, which allows us to talk about the scalar product in the case of spacetime particularly. If you're not familiar with this notation, we're saying I have previous videos on Lorentz invariant quantities that are on this playlist. There's lots of other YouTube videos around, and there's also good documents on the web. So if you're not familiar with this notation, I would recommend checking it out. But we end up concluding that q squared is equal to Lorentz squared multiplied by c squared minus v squared. Now the Lorentz factor has an equation which we covered also earlier in this playlist, and you can find the equation easily online. And then if you square the Lorentz factor, you can easily show that q will have to be plus or minus c. Now, when talking about the size of a full vector in special relativity, because of the possible confusion that kind of, the size, depending on how you define the full vector, can sometimes be negative. You'll sometimes see kind of like the size of a full vector, if you want a positive answer, to be written as the full vector in the middle with two parallel, with a pair of parallel lines either side of it. But no matter what notation you want to use, essentially q is plus or minus c. And c is a Lorentz invariant quantity, so all observers, so both you and let's say the driver of the truck, agree on the speed, and that's not too surprising because we want the size of full velocity to correspond to a Lorentz invariant quantity. At least that should be possible based on our geometry of space-time and how we construct full vectors. So that itself isn't too much of a surprise, and the only Lorentz invariant speed, so the speed that both you and the truck will agree on, no matter how quickly the truck is moving, is the speed of light. So that's a summary for this bit of the video, and now we'll move on to a cheat way to find the size of full velocity without having to even worry about the components of full velocity. A nice trick I found, and also a good way to get to the conclusion really quickly. Although I like doing it by considering the components, because that really emphasizes the importance of reference frames in special relativity and being careful what time interval we're talking about. So, having gone through a fairly detailed way to find the size of full velocity, we're now going to find it in a slightly cheap method. I say cheap method because we're going to use the definition of full velocity. We're not going to actually look at the components of full velocity explicitly to do this. So remember, full velocity is the rate of change of full position with respect to proper time tau. And because of this, the size of full velocity q is going to have to equal the size of the change in full position divided by the size of the time interval d tau. but the space-time interval, the change in full position, at least if we're looking at the change in full position where we're measuring the full position of each point in space-time from the origin of the stationary observer's space-time axis, then the change in full position is just equal to, well, essentially it's equal to the space-time interval between one event and the other event, so between the 2 points in space-time. But we have before an equation for the space-time interval, so we're going to use that, and the change in time as well, just equal to the change in time. Now, when we looked at full position earlier on in this playlist, we said that the Lorentz invariant quantity associated with full position is the space-time interval, ds. And because it's a Lorentz invariant, we can measure ds in any reference frame we like, and all observers will agree on this space-time interval, even though they might use different quantities to describe the space-time interval. So if we're looking at the space-time interval between events from the truck's perspective, the space-time interval will equal plus or minus c d tau. If we're talking about the space-time interval from the stationary observer's perspective, it will be written in terms of spatial distances and time intervals dt, but the value will still end up equaling for the space-time interval plus or minus c d tau. Now, I put plus or minus because because ds squared is going to be c squared d tau squared, but ds itself will be plus or minus c d tau. Again, thanks to the properties of square rooting. And then plugging ds into our formula for q squared, we end up with q, the size of full velocity, is plus or minus c, like we had before. So that's a cheap way to do it. But the nice thing about this way is it links full velocity to full position through the space-time interval. And the space-time interval is very special because we saw that as the first Lorentz invariant quantity. Well, I suppose technically after saying the speed of light is Lorentz invariant, but the space-time interval being Lorentz invariant leads to the idea of time dilation, and we use time dilation to find one component of the Lorentz transform matrix and therefore be able to find all the others. So much of relativity does ultimately boil down to time dilation and the space-time interval. So this derivation wraps a lot of stuff with four vectors up quite nicely. So that was a kind of cheap way to get there. Now I'm going to give you a challenge. And this challenge is to make this video more interactive, at least as much as possible. It's interesting challenge because kind of physics is a mix between, at least theoretical physics, well-established facts about reality, and a human kind of description of those facts. Or at least as close to facts as you can get in science, because you always have to be open to changing your view if new evidence comes along. But because of this interesting balance, things like full velocity can actually be described in many ways. So we said earlier that you could, if you wanted to, define velocity to be dx by dt instead of dx by d tau. In other words, you could consider the rate of change of full position with respect to time from your own reference frame, as opposed to what you would seem to consider to be time from the truck's perspective. And so my challenge is, if we define for velocity to be this, so we define it to be dx by dt, then can you get an expression for dx by dt and therefore show that, firstly, assuming the truck doesn't accelerate, the size of full velocity will be a constant, at least with respect to time. However, the size of full velocity would no longer be a Lorentz invariant. So my challenge for you is to find an expression for dx by dt and show these two properties of it. And it's these kind of like small mini activities which, ultimately theoretical physics is full of, because theoretical physics is just the result of doing many of these things and playing with different ideas. So I feel like this will hopefully be fun, but also for those of you who would like to get kind of started on exploring physics for yourself, to give you a kind of like challenge and let you discover something for yourself and have a play with some of the ideas we've discussed. So I hope this video has been enjoyable. I will do a video on another full vector called full momentum at some point, but this is everything for this video. And as always, any suggestions, let me know in the comments, and I will go and do what I can to make these videos as good as possible. And also, if there's any material you would like me to cover, as always, let me know kind of down below. I've got a few plans for this channel, but ultimately I want to kind of cover content that this channel's community, so you and everyone watching will find enjoyable and exciting, because I'm hoping to show that physics is more than just electronic circuits. As interesting as electronic circuits can be, but there's a lot more to the picture than what is kind of covered at the GCSE syllabus and even the A-level syllabus. So I hope this video has been fun, and hopefully see you for another video soon.